Actually, the first part is already out, Knaster and Friends 1. The first paper focuses on close colorings and pre-calibers, and as you see, it's already published. The second one focuses on the C-sequence number, and this is going to be a big part of our talk today. It will be finished soon. And the third part, where it's still far from being finished, it will deal with subadditive colorings and stationary layered posets. And I don't think I will have much time to talk about this today. Okay, some conventions. We fix some conventions. Kappa and lambda are infinite cardinals. We write reg kappa for the set of regular cardinals, infinite regular cardinals below kappa. We denote by E, oops, I have to get used to the remote. E kappa greater or equal chi for the set of all ordinals alpha below kappa of cofinality at least chi, and similarly for greater, strictly greater than chi. A to the chi is the subset of A of cardinality exactly chi, and the same definition is valid for strictly smaller than chi. And finally, for subsets A, B, non-empty sets of ordinals, we write A less than B just to mean that the sup of A is below the mean of B. So we start with chain conditions. This picture was taken in Cornell. Justin sent it to me. And CCC is one example. Okay, so we have some partially ordered set P. And let me just introduce this ad hoc notation. The meet of X, given a subset X of our poset, the meet of X are all elements Z which are below all the elements of X. It could be an empty set, but if X is empty, then this is a non-empty set. Okay, so in other words, we can define compatibility this way. Two elements X, Y of our poset are compatible if the double tone consisting of X and Y is non-empty or has a meet. So now we arrive to the basic definition of the kappa chain condition. P satisfies the kappa CC if and only if, whenever you're given a set A of cardinality kappa, you can find a subset X of cardinality 2 that has a meet. So basically, if you give me a subset of size kappa, I can find two elements that are compatible. This is kappa CC. And then we arrive to something a little bit stronger. This is the kappa Knaster property. For every subset of size kappa, there is a subset B of size kappa, such that for any two elements from B, we have a compatibility. This is kappa Knaster. Now something a little bit stronger, pre-caliber kappa. So P has pre-caliber kappa if and only if, whenever you give me a subset A of size kappa of my poset, I can find a subset B of size kappa, such that for every finite subset of B, there is a meet. And finally, a stronger chain condition. This is due to Sean Cox, even though I guess it was implicitly defined by other people before that. P is said to be kappa stationarily layered if and only if the following set, the set of all subsets of P of cardinality less than kappa, forming a regular suborder of P, this is a stationary subset of all subsets of P of size less than kappa. This is called stationarily layered. Okay, so let's talk about the product order, or in other words, the coordinate-wise order. If you are given two posets P1, P2, you can look at the product, and the product is just, as I said, coordinate-wise. So if you have x, y, and x prime, y prime, for x prime, y prime to be above x, y, you just have to be above, x prime has to be above x, and y prime have to be above y. So in both coordinates, we require to dominate. And of course, I define it for two, but you can define it for longer products as well, including infinite products. So here is a very basic question. Suppose you have P1 and P2, two kappa CC posets. Must the product satisfy the kappa CC? And there is an obvious sufficient condition. Well, if one of the posets is moreover kappa Knaster, then definitely the answer is yes, right? You project to one of these coordinates, and either the cardinality there is less than kappa, and then definitely you can use the kappa CC of the other side, or it has cardinality kappa, you apply Knasterness to this coordinate, and then you go to the other side. But what happens in general? In general, I can define an axiom. So I'm defining an axiom, C sub kappa, to say that the product of any two kappa CC posets is again kappa CC. And notice there is a very easy reduction requiring that the product of any two kappa CC poset is kappa CC is the same as requiring that the square of any kappa CC poset is kappa CC. And you can just take the disjoint sum of the two posets and get a single one, giving you the example. So let's talk about some of the basic facts. Some of them are well known, some of them are less known. What's the status of C sub kappa? C sub kappa holds for kappa equal Aleph 0, right? This is very easy. Let us moreover show that if you have a poset which satisfies the Aleph 0 CC, it actually satisfies the Aleph 0 cluster property. Why is it so? Well, given a subset A of my poset of size kappa, in this case kappa is Aleph 0, I can define a coloring of pairs. I can send any pair xy into color 1 if and only if they have a meet, whether if they are compatible or 0 otherwise. And now I'm invoking Ramsey's theorem and I'm getting a subset B of the same size, which is C homogeneous. Now, since this set B has size kappa and the poset satisfies the kappa CC, there will be some two elements in B which are compatible, but the set is homogeneous, so actually every two elements will be compatible. So we verified that C kappa holds for kappa equal Aleph 0, but of course this also works for weakly compact, because all I was using is Ramsey's theorem. I put here in red. This is all I'm using, of course, for the argument. And we'll come back to discussing weakly compact cardinals along the whole talk today. One other observation is that C kappa is actually a theorem, it's a fact that it holds for every kappa which is singular strong limit. Why is it so? Because we can combine two facts together. Erdős and Tarski proved that if you like, the least cardinal kappa for which the kappa CC holds for a poset has to be a regular cardinal. So if you have kappa CC where kappa is singular, you actually have lambda CC for a smaller cardinal lambda. But also, there is a theorem of Kurepa that if P satisfies the lambda plus CC, it will satisfy, the square will satisfy 2 to the lambda plus CC. So if lambda was a strong limit, if kappa was a strong limit, you are still below kappa. So putting this together, you get that singular strong limit satisfies this axiom of productivity of the chain condition. Now let's move forward to kappa equal Aleph 1. This takes us to a question of Marchevsky from 1947. He's asking, is C Aleph 1 a theorem of Z of C, or in other words, do we have productivity of the CCC? This is a well-known question addressed by many people. The first observation in this vein is due to Kurepa. He proved that if there is a Suslin tree, then there is a counterexample to productivity of the CCC. And then many people, I don't know exactly how to trace all of them, but many people realize Martin's axiom MA Aleph 1 implies productivity of the CCC. And here there is a little bit of a converse. There is a theorem of Velichkovich and Todorcevich in 1987 characterizing Martin's axiom at the level of Aleph 1, MA Aleph 1. This is the same as asserting that every CCC poset has pre-caliber Aleph 1. And then there are more results. There are results involving forcing, so you can force to add random wheels or coin wheels and get counterexamples to productivity of CCC. And the last thing is that you can use cardinal invariant. So if you have something here, if you have CH, then Galvin constructed from CH a counterexample to productivity of CCC. And Todorcevich reduced this to this cardinal invariant, the bounding number equal Aleph 1. So from some sort of cardinal invariant assumptions, you can cook up counterexamples to productivity of CCC. I think it's worth mentioning that it's still open whether MA Aleph 1 is equivalent to the assertion that the product of any two CCC posets is CCC. This is open since forever. Okay. Now let's talk about uncountable cardinals, uncountable regular cardinals. Here there's a theorem of Todorcevich from 1985 showing that there are actually class many cardinals, regular cardinals, for which the productivity of kappa chain condition fails. You don't have, there will be counterexamples for class many cardinals. And then there are more results that dealing with successor of singulars. So Todorcevich was using scales before scales were proven to exist, so under some cardinal arithmetic hypothesis, which eventually was eliminated by Shelach, who proved that there is a scale. But you can use scales to get a counterexample to productivity of the chain condition at the level of successor of singulars. So for every successor of a singular cardinal, there is if lambda is a singular, there is a lambda plus CC poset whose square is not lambda plus CC. Now what happens about successor of regulars above Aleph1? Here there is a sequence of works of Shelach, starting with Shelach 280 and culminating in Shelach 572, showing that indeed there are counterexamples for any successor of a regular greater than Aleph1. So the latest result, the hardest, I guess, result has to do with Aleph2. So he proved in ZFC, this is a theorem from 1997, that there is an Aleph2 CC poset whose square is not Aleph2 CC. So putting this together, we now see that productivity of the chain condition breaks down at any successor cardinal greater than Aleph1. At Aleph1 we have Martin's axiom that gives a positive answer, CH or B equal Aleph1 a negative answer, but as soon as you go to Aleph2, any other successor cardinal will fail to satisfy this. And this raises a very natural conjecture due to Todorcevich. He conjectured, I was promising you that we are going to discuss weakly compact cardinals, he conjectured that C kappa actually characterizes weak compactness for any regular cardinal greater than Aleph1. And this is still open. I have a partial result from 2014. I showed, well, that if C kappa holds, then kappa is weakly compact at least in L. Or combinatorially, the proof shows that you have the failure of squared kappa, and also, this is another theorem, you get that every stationary subset of kappa reflects. But what happens if you are looking at longer products? What happened is that, I guess, Philip Lucke realized that we don't know how to answer Todorcevich's conjecture, we don't know how to answer the question, so maybe we should look at other variations of the chain condition, not just chain condition kappa CC, maybe kappa knuster or stationary layered and such chain conditions. So he teamed up with various people, and I'm going to mention 3 results of Lucke and his colleagues. So the first one is the characterization of weak compactness. So they proved that for every regular uncountable cardinal kappa, kappa is weakly compact if and only if every kappa CC is moreover kappa stationarily layered. So this captures weak compactness. And they also proved a non-characterization theorem, some negative result if you like. If you start with a weakly compact cardinal, then there is some cofinality preserving forcing extension in which the property of being kappa knuster is preserved under products of any lengths below kappa. So this looks like a feature which is very close to being weakly compact, but apparently this doesn't characterize weak compactness. You can start with a weakly compact and go to an extension in which the cardinal is not weakly compact, but you still have preservation of kappa knusterness under a very long product. And then in another paper of Lucke with Lambi Henson this time, they show that if you are in the situation with the kappa knuster being closed under a long product, then square must fail. So the assumption of starting with weakly compact was necessary, because as soon as you have the property of kappa knuster being preserved under long products, then you had to start with a model with a weakly compact. Okay? So now I'm going to focus really, kappa will always denote a regular uncountable cardinal. And I'm going to compare the 2 approaches. There is the approach of Galvin. So Galvin, his way of producing a counterexample to productivity of Aleph1 CC, the CCC, was as follows. It's quite general. He constructs an anti-Ramsey coloring at the level of kappa, which is quite interesting because we saw that Ramsey theorem implies productivity of the kappa chain condition. So the idea of Galvin was take a very strong failure of Ramsey theorem. If there is a very strong anti-Ramsey coloring, there is a way to read from it a kappa CC poset whose square is not kappa CC. And then the key was, so he used the GCH assumption to show that such colorings exist. But the key was that Shelach found in 1997 that you can construct in ZFC such a coloring. You can construct a coloring satisfying the anti-Ramsey statement of Galvin, and from which you get a poset which is Aleph2 CC whose square is not Aleph2 CC. So this had to do with non-productivity of the chain condition. What about the knusterness? So this is what was done in the work of Lambi, Henson, and Lucke. they were constructing non-spatial kappa Auenstein trees, and they used them to derive kappa cluster posets whose infinite power is not kappa cc. You cannot expect the finite power to be not kappa cc, but the infinite power would be. I mean, it's conceivably would be. So their approach wasn't to use coloring, they are using trees. And how they connect it to weakly compact cardinals? Well, they were using the assumption of square round brackets kappa to construct such non-spatial trees. So you construct non-spatial trees, you look at the forcing to specialize them, and you show that they satisfy a kappa clusterness to some degree, but not in the infinite powers. That was the approach. So you see there is a gap here, because Shelach was able to handle even Aleph2 in ZFC, whereas here, if you want to handle even Aleph2, you have to assume some extra. So we would like to obtain the conclusions of Lambi, Hanson, and Luque from ZFC. For instance, our test case would be, can you construct an Aleph2 cluster poset whose omega power is already not Aleph2 CC? And of course, we cannot use this approach of square and trees because in ZFC you cannot prove they hold. So the idea is to revisit Galvin approach and to see what would be the coloring axiom that will give us maybe, possibly a counterexample in ZFC. So coloring would be the way. So here, this is Galvin's poset. I'm starting with Galvin's poset. So you start with any coloring C of pairs of kappa in theta many colors, theta is some regular cardinal below kappa, and we derive the following poset. You look at all possible pairs x, I, where x is a finite subset of kappa and I is some fixed color, but you only look at these x's which are homogeneous for C, not just homogeneous, actually getting color I. So maybe X is an empty set, then there's no problem. Maybe it's a singleton, but as soon as there are two elements there, then all the colors they get there is always I. This is the definition of Galvin of the poset. And now I'm going to define a variation which is very natural. I'm going to call it Q. Here I'm going to look at all finite subset of kappa, where the color every two elements gets in X is at least I. So I don't require it to be equal to I, I require them to be at least I. That's the only change in the definition. And the ordering is as follows. Xi extends yj if x is just a superset of y, and I is the same as j. So it's like a lottery sum of different posets, each one dealing with particular color. And the key feature here is that the square of p fails to have the kappa cc, and the theta power of q fails to have the kappa cc. I didn't assume anything about the coloring. I'm just saying that this is always the case. Let's see why. Well, in the case of p square, look at the following kappa size subset of the second power. I'm looking at singleton 0, singleton 1. I'm claiming that this is a kappa size antichain in the square. Why is it so? Well, given any alpha and beta, they get some color I, say it's 1. And then if you look at the other coordinate, right, say coordinate 0, then they will not be compatible. So there has to be one coordinate where they are incompatible. So the square is not kappa cc. What about our variation, the Q? Well, look at this kappa size family. You look at all the sequences of singleton, I goes all the way up to theta. This is an element of the theta power of Q. And again, I'm claiming that this is an antichain because given alpha and beta, I look at the value they get, say I call it I, then if I go a little bit higher than that, say I plus 1, then they are already incompatible in this coordinate. Okay, but all of this is really given to us for free. I'm not doing anything special to get it. So the heart of the matter is actually to construct the C I'm starting with in such a way that the corresponding poset P here would be kappa cc, because I know the power, the second power is going to be not kappa cc. Or in the case of Q, I want to maybe make it kappa cluster all the way up to theta, because I know it will fail at theta. So really the question is, what should be the features of C to make the corresponding posets very nice, like having kappa chain condition or even being cluster. So you do a little bit of reverse engineering process and you figure out what are the features of the colorings that will take care of this. So the poset P, as I said, was analyzed by Galvin, and this gives rise to, some of you know this principle PR1, this is some coloring axiom. But today I'm going to focus on our poset Q, so let me give you a definition of whatever is needed to make the poset cluster. So this is our poset Q, this is our coloring, and now I'm claiming the following. Q is going to be kappa cluster if and only if it already has pre-calibrated kappa, if and only if our coloring C witnesses an axiom involving kappa and theta as follows. And here I'm going to draw a picture. So the axiom is as follows. There is a coloring of pairs. This is kappa. This is theta. And now someone gives me a family of finite sets, kappa many pairwise disjoint sets. This is the A. And someone gives me a color, I. And the requirement is as follows. I require that whenever I'm in such a situation, you gave me a family A of kappa many pairwise disjoint finite sets, and you gave me a color I can find a subfamily B. So I'm taking this one, and so on. So a subfamily, but again of size kappa. With the property that whenever I'm taking two sets A and B from this family, and I look at the color they get, then the color is going to be at least I. For any choice of two, the color will be at least I. Okay, so this is the outcome of the reverse engineering of our poset Q. If you ask yourself what's needed to make the poset kappa cluster, this is exactly the axiom, U kappa theta. Is it clear? Now, you may also want the poset to be a little bit better than chain condition. Maybe you also want it to be very close or something. So there is a Chi-closed variation of the poset. So you look at all pairs xi, where x now is a subset of size less than Chi. Automatically, this poset is going to be Chi closed, actually Chi directed closed. So for this to work, you just have to allow, instead of talking about finite sets, you have to allow sets of any fixed size Chi prime below Chi. Everything otherwise works the same way. So I think we are ready to define our axiom. As I promised to Ralph, only 4 parameters today, not more than that. So here is our axiom. U kappa mu theta Chi tells you that there is a coloring C of pairs of kappa in theta many colors. That whenever you fix some value Chi prime below Chi, and you're given a family of kappa many pairwise disjoint sets, each one of this fixed size Chi prime, and you give me a color I below theta, I can find a subfamily B of size mu. This is the last parameter I just inserted, such that the color you get on rectangles is at least I for any 2 elements from this B. So the proposition is that if you have a coloring witnessing this axiom, U kappa mu theta Chi, then the corresponding poset Q satisfies the following features. We already know it's not going to be kappa CC, the theta power. But if mu is equal to, then it's readily seen that you get that Q to the tau is going to be kappa CC for every tau below the mean of Chi and theta. And mu is this how many figuring out you can do when you move from you are giving kappa many and you have to pick mu many. So if you just pick 2, then this is kappa CC. But if you pick kappa many, then you get clusterness. And actually I show you that, I told you that clusterness is the same as pre-calibrated kappa. And finally, there are more nice features of this poset. This poset is well met, it's Chi-directed closed, it has greatest lower bounds. So this is really a nice axiom. At the moment, it looks promising that maybe we can use it to produce counterexamples in ZFC. So 2 is always about getting, chain condition, and kappa is getting kappa many, and so this is like clusterness. Any other questions? Okay, so I'm already arriving at a conjecture. Maybe it's too early, but I feel like maybe this characterizes weak compactness. So the conjecture is that for kappa regular and countable, kappa is weakly compact if and only if you have an unbounded coloring. You don't have an unbounded coloring of this form. So let's parse it. What does it mean, U kappa 2 omega 2? It means that you can color pairs in kappa in omega many colors, such that on any subset of size kappa, you will get infinitely many colors. And when I'm talking about weak compactness, I'm talking about Auenstein tree. So in simple words, this is my conjecture, is that as soon as you have a kappa Auenstein tree, there will be a coloring of pairs of kappa in omega many colors, where on any set of full size, you get infinitely many colors. But why should I conjecture such a thing? Because we already have some partial results. So the first observation is that if there is a kappa Auenstein tree which is a little bit better, it has an omega ascent path, then you get u kappa tau omega and even omega, meaning you can even handle finite sets, not just singletons.
What is an omega ascent path?
It's like a path, but it's in the with omega. So this is your tree. You take omega copies of your tree, and then at each level alpha, you choose someone here, someone there, and so on. And the ascent path means that you can do it for every level, alpha, beta, and so on. And the property is that with this choice, you would get that every such sequence dominates another one from one point on. So it's like a branch, but it's branch on the omega power. If you look at the reduced power, for instance, there is a branch. It's not Auenstein anymore. So such a tree gives rise to a nice coloring. Another partial answer we observed with Todorcevich when I visited him just 2 months ago. If there is a coherent kappa Auenstein tree, then again we get this nice coloring, but you can also show that this doesn't give you the stronger one. So again, 2 has to do with kappa CC, and kappa has to do with kappa cluster. So there is an indication maybe our conjecture is correct. Maybe this is another way to characterize weak compactness. But now let us systematically inspect the parameters and understand how it goes. I mean, we are led to study this coloring, so let's do it. So let me tell you a few things about the second parameter. Second parameter is the size of the subfamily I'm thinking out, right? The B here. If on any family of size kappa you can find 2 elements getting color as high as you like, then you can find infinitely many. This is just an application of Dushnik-Miller. The other thing is that if the coloring witnessing this is closed coloring, then you can go all the way up from 2 to kappa. What do I mean by closed coloring? I think it's a very natural definition. We say that the coloring is closed if whenever you fix some beta and some I, and you look at all the alpha up to beta getting color at most I, then this is a closed subset of beta. So it turns out that if the coloring is closed, then you can move from something corresponding to kappa CC to something corresponding to kappa cluster. Now let's inspect the third parameter. Third parameter is the number of colors. Definitely you can be unbounded in kappa many colors because just take C alpha beta to B beta, or alpha, whatever you choose. You will always be as high as you like. So this means that this is non-interesting. The other observation is that if you have a coloring working for theta many colors, you can definitely also go to cofinality of theta and vice versa. So that's also obvious. But now, what about monotonicity? What about getting, if you have, say, aleph1 many colors, can you get aleph0 many colors? Usually in negative partition relations, in colorings, you can go from one coloring to another, or if this is positive, you can go up by a colorblind argument. But here it's unclear whether handing aleph1 gives you a way to go to aleph0 or vice versa. And in fact, okay, so I'm going to only focus on regular cardinals below kappa because of these 2 bullets. But in fact, there is no monotonicity. So you can cook up, in fact, in ZFC, if there is assuming large cardinals, but there is a combinatorial statement here. If lambda is a singular limit of strongly compact cardinals, then the only colors that will satisfy this axiom would be the colors with exactly cofinality of lambda. So there is no monotonicity at all. It's like if you look at only all regular cardinals, it's a singleton. Now let's talk about the fourth parameter. Here there is an observation that if you can handle double tones, you can actually handle finite sets. And the next thing is that the level of successor cardinals, if you can handle singletons, you can actually handle sets of size less than cofinality of lambda. This is, I guess, already non-trivial, but this uses, some of you know my work of transforming rectangles to squares. So I'm using this as a black box to somehow transform these sets into singletons, and then you just compose together very nice colorings, and this works. And this is optimal. You won't be able to push it for more than cofinality lambda. We have very concrete counterexamples. You cannot more. You could do it for cofinality lambda, but will not be able to do it for cofinality lambda plus. I guess I should mention that when you move from a coloring handling, say, singletons to handling finite sets or more than that, you are not expected to do it with the very same coloring. There are class many cardinals kappa theta where it will satisfy the axiom with 2, but not satisfy the axiom with 3. So you have to cook up another one. I guess this is natural. And here we have another theorem saying that if there is a closed witness for coloring with 2, you can also do it for cofinality lambda, many sets of size less than cofinality lambda. And unfortunately for this, I cannot just use my theorem as a black box. I really have to redo it in this context of unbounded colorings. And we did it in the first paper. And so now we have this theorem about the fourth parameter. OK, so far, we just inspected the very basic features of the parameters. The next thing to do is to construct counterexamples. If I can construct colorings in ZFC, I will be able to get counterexample to clusterness. So we have a few more findings, of course. So the first finding is that at the level of successor of regulars, we actually get all possible variations. All of them are provable in ZFC. So for every regular cardinal lambda, every regular cardinal theta up to lambda, there is a coloring witnessing u, lambda plus, theta, lambda, which is more overclosed. This is the best you can hope for, and you get it in ZFC. In case you wondered, some of you are also interested in trees, you can look at the corresponding tree of this coloring. It's not going to have a very specific feature. It could be special, but it can also be almost Suslin. We produce two different examples. You still have this feature, but this feature doesn't decide the type of the tree that you're going to get. So the corollary is that in ZFC, there is an Aleph-2 cluster poset whose omega power is not Aleph-2cc. Okay, this is analogous to the result of Shelach from 1997. More generally, this works for any regular cardinal because of our theorem. But notice that we can also handle directed closed posets. So this means that in CH, assuming CH, there is a poset which is more over sigma closed. Under CH, there is a sigma closed poset which is Aleph-2 cluster whose omega power is not Aleph-2cc. The analogous question for the Aleph-2cc is still open. This is not known. We don't know whether CH gives us a sigma closed poset whose Aleph-2cc whose square. It does. What's the argument?
I tell you exactly 2 years ago.
Okay, we need to discuss it and verify it. I'm missing something. Okay, thank you. What happens at the level of successor of singulars? Well, as Saron said in the meeting 2 years ago, I don't want to repeat what he was saying about successor of singulars, but they are particular. So with successor of singulars, the situation is much, much harder, but we have plenty of results. Each one is like standing on its own. You have to do it separately. Any of these hypotheses suffices to construct a counterexample. I mean, such a coloring with theta many colors, cofinality lambda, and it's going to be closed. If you look at that, maybe you say, well, it's obvious what he's doing here, right? He's taking a list of all subsets of lambda plus of size lambda, and you do some diagonalization. Well, this doesn't work, right? Because I want a closed coloring. These typically work for coloring that is said, if you give me a family of lambda plus many sets, I can find 2 that satisfy something. Here I want lambda plus many such. So really the proof is not what you would expect. We are cooking up some particular ladder system using diamond and club guessing and walking along this particular sequence to construct the counterexample. The other assumption has to do with failure of simultaneous reflection. This is based off ideas of Todd Eisworth. He was addressing the usual question of negative partition relation for successor of singulars, and we use the same ideas to handle our variation. We can also handle some extreme cases like theta equal omega. We can just do it in ZFC, or theta equal cofinality of lambda. If our singular cardinal has to happen a successor cofinality, then we can also handle colors below the predecessor of the successor. And assuming some cardinal arithmetic, we can also handle all of them up to the cofinality of lambda. So the upshot here is that if the class of kappa cluster poset is closed under omega powers, again, this is in ZFC, then kappa has to be inaccessible. We handle successor of regulars, we handle successor of singulars. This is already what we know at this stage. but we have more results, not just for kappa inaccessible, but in general, you would get this sort of coloring, assuming that you have a narrow enough square, or if you have an index square, or if there is a non-reflecting set concentrating of points of cofinality at least 3, or if kappa is inaccessible, then you just need the set to be stationary and non-reflecting at inaccessibles. So we have a lot of sufficient conditions for producing counterexamples, but it looks like we are led to actually study a cardinal invariant. Just like Stevon was moving from C equal aleph 1 to B equal aleph 1, we are led to consider some cardinal invariant here. And the cardinal invariant is very naturally attached to the omega power of clusterness. So we are motivated by another characterization of weak compactness. This is the theorem of Todorcevich. You can characterize weak compactness as follows. For strongly inaccessible cardinals, being weakly compact is the same as the following. Whenever you take a C sequence, so a C sequence is just, you have your cardinal kappa, for every ordinal alpha you attach some club C alpha. And now the characterization is as follows. You get that the cardinal is weakly compact if and only if whenever you take any C sequence, there will be a subset delta which is cofinal in kappa with the following property that whenever you stop at some, so you get some cofinal set delta, with the property that whenever you look at here at some alpha, there will be some beta greater or equal than alpha, I'm calling it B of alpha, where your set up to alpha is actually this C B of alpha up to, I'm chopping it up to level alpha. This is the same as weak compactness. If you look at it in the language of trees, it's more natural because you construct some sort of a tree, you look at its downward closure, and then basically elements at level alpha are some restrictions of elements of higher level. So the statement is as follows. For every C sequence, C beta, there is a cofinal set delta and some function such that every initial segment is just the same as the some higher maybe club up to exactly alpha. So our idea was to look at that and to make a cardinal invariant capturing this idea. And what we would like to do, we would like to measure how far we are from being weakly compact. We want to know how far, we start with any cardinal kappa, and we would like to know how far is it from being weakly compact. So it makes a lot of sense for inaccessible, but actually it turns out it makes sense also for successful cardinals. So here our definition. This is the cardinal invariant C sequence number of kappa. So if kappa is weakly compact, it's as close as possible to being weakly compact, so we assign it to be 0. And otherwise, Chi kappa is defined the following way. It's the least cardinal Chi such that for every C sequence, you can find a cofinal set of size, subset of kappa of size kappa, such that every initial segment is covered by Chi many elements of your C sequence. Okay, so the larger, the more sets you need, it feels like you are more far from being weakly compact. Weakly compact means 0, and then you can start looking of how far you are from being weakly compact. Notice the definition, it's well defined. You can always find such a Chi. It would be at most kappa, but actually it would be at most, if kappa is a successor, it would be the predecessor of kappa at most. And why we were led to discover or to discuss this cardinal invariant? Because there is a very fundamental theorem of Todorcevich dealing with the function counting the number of steps of a walk from one ordinal to the other. He showed, if you look at the proof, this really readily shows that this function ρ2, that counting the number of steps, is a witness for U kappa kappa omega Chi of kappa. So this cardinal invariant is really capturing what the proof gives. So as a corollary now, we are going a little bit further. We see that if the class of kappa cluster positives close down the taking omega powers, then Chi of kappa is less than omega. Because as soon as it's omega, we have U kappa kappa omega omega, and then we have our poset that will give the counterexample. So the question is, the assumption Chi kappa being less than omega, is this a large cardinal property? And what happens if Chi kappa is less than the sup of the reg, which is the obvious bound? And another question is whether Chi kappa could be a singular cardinal. So let me show you that there is a model in which Xi kappa is equal to 1. You are very, very close to being weakly compact, but not quite weakly compact. And this is the Kunin model. Kunin showed that there is a model in which the cardinal kappa is a Suslin tree away from being weakly compact. This is a model where there is a Suslin tree, so it's not weakly compact. But when you force with the Suslin tree, now kappa is weakly compact. And in this model exactly, you are very, very close to being. The Xi of kappa is exactly 1. Why is it so? As I said, it's not 0 because there is a Suslin tree. But now take any C sequence in your model. It's also a C sequence in the extension because you force with a kappa CC forcing the Suslin tree. But in the extension, you do have the theorem of Todorchevich, right? That you can find a club, you can find a delta with the property that every initial segment is the initial segment of one of the elements of here. But if this is an initial segment looking like that and this is a club, then this has to be a club as well. It's a closed set. But if it's a club in a kappa CC extension, it has a ground model club subset of it. And the ground model club is exactly what you need in your model to have being a subset. Here it was equality, but here it's a subset. So now we have a model where Xi of kappa is 1. Can we have a model where Xi kappa is omega? Can we have a model with Xi kappa is omega 1? So the answer is yes. If you start with any model with Xi kappa equals 0, namely a weakly compact, there is a cofinality preserving forcing extension, or you start with any prescribed value in which the Xi kappa would be. You would be exactly theta far from being weakly compact. Now what about successor cardinals? So as I said, Xi of lambda plus would be at most lambda, but you can also show it its least cofinality of lambda. Is there anything better you can say? Well, for regulars, there's nothing you can say more, but for singulars, there is more you can say. So if lambda is the singular limit of supercompacts, then Xi lambda plus is as small as possible. You are being very close in a sense to what I was calling to be weakly compact. But also you can force to increase the value to any theta greater than cofinality of lambda. Now remember I was asking you whether Xi of kappa could be a singular cardinal. So the answer here is yes as well. It is consistent that Xi of aleph omega plus 1 is exactly aleph omega. And starting with a supercompact, we can also make it omega. So I'm coming back to my question of how large. Suppose that kappa cluster is productive under taking omega power. It's preserved under omega power. How large is this cardinal? So we have more theorems. So you always have reflection. You see, this is a ZFC theorem. I define for you a cardinal invariant, Xi of kappa, and I can just prove, just from this definition, that any finite collection of subsets of kappa of cofinality greater than Xi of kappa will reflect simultaneously. Okay? The other thing is that if Xi of kappa collapses below omega, it actually has to be either 0 or 1. And the other thing is if kappa is inaccessible and Xi of kappa is collapsed, then kappa is at least omega malo. If Xi of kappa is 1, then you have failure of narrow squares, and you have diagonal reflection. Just this combinatorial assumption of Xi of kappa equal 1 gives you diagonal reflection. Putting this together, you get that in L, you have the dichotomy, right? Either you are 0 or you are as large as possible. If you have a narrow square, then you get the Xi of is as large as possible. And most importantly, if Xi of kappa is 1, kappa is greatly malo. So this is another improvement of our result. We get that if the class of kappa cluster poset is closed under taking omega powers, then kappa is greatly malo. But once we understand all of that, we were led to actually look not at the soup of all possible C sequences, we were led to consider the C sequences each one by himself, and this is the spectrum. So for a given C sequence, we can ask what's the Xi value of this particular C sequence. You give me a C sequence, what's the least size of a family when you can find a cofinal set such that every element, every initial segment of the cofinal set is covered by Xi many elements from your particular C sequence. So we define the spectrum, we look at all possible values you get well, we are discarding 0 and 1 because this is not no interest. So the first theorem is that the soup is equal to the max. The definition I gave you before, when I'm ranging over all possible C sequences, actually there will be a single C sequences witnessing the value of the C sequence number. The other observation is that there is a minimum, and the minimum is as small as possible. It's going to be omega. And the other theorem is that, well, if Xi is in there, then also the cofinality will be there, but it doesn't work the other way around. And now there are plenty of open problems. So must the spectrum be an interval? I have no idea. Must it be closed? I don't know. I try to prove that. I don't know how to show it that the limit point has to show up there. And suppose you have a limit uncountable cardinal in the spectrum. Must it be an accumulation point? Could it just show up there without any initial segment leading to it? I really don't know. But we are getting something which is quite unexpected. And I'm not talking about the fact that the prices are given in binary system. I'm talking about the fact that we are led to discuss chi of kappa because we were looking at omega powers. But it turns out that the spectrum also captures higher colors, not just omega. So we have this equivalency. So for every regular cardinal theta, T will show up in the spectrum if and only if there is a close witness to U kappa kappa theta theta. So we really define all of this just because we cared about U kappa kappa omega and this extra parameter, but it turns out that they come together. And the proof is quite complicated because even if you come up with a coloring, it's not going to be completely close, and then you have to do a little bit of smoothifying it to make it close. You have to walk along some things. I think the proof is really interesting. But the corollary, we get quite a lot of information. For success of regulars, you get that the spectrum contains all regular cardinals up to kappa. Also for non-Malloy inaccessibles, if you have a narrow square, or non-reflecting stationary set gives you a lot of information about the spectrum. But I feel like even though we have quite a lot of information, there are still many open problems, so I decided to basically assign each one of you an open problem. There are many conjectures. I decided to give 7 of them. I don't know whether this is really a conjecture, but I'm formulating it in a way which this is the case that we know that it's possible. So it's at least I know all of them are possible. So the conjecture is as follows. If chi of kappa is 1, then there is a forcing extension in which chi kappa is equal to 0. You cannot be 1 without really becoming weakly compact again, being resurrected as a weak compact in the extension. If chi kappa equal 1, then I believe that there has to be coherent kappa Aron-Chain tree. And if kappa is inaccessible somewhere in between 1 and kappa, and these values, then there will have to be a kappa Aron-Chain tree, which is containing a chi kappa ascent path. It just looks like they come together, as far as I can tell. I also hope to answer the question whether any instance like this have to be witnessed by close coloring. In terms of chi kappa being singular, I showed you that chi of aleph omega plus 1 could be aleph omega. But I don't know whether it could be that chi aleph omega 1 plus 1 would be aleph omega. So the conjecture is that the cofinality has to be the cofinality of the predecessor. So for instance, for kappa inaccessible, maybe this means that you cannot be singular at all. The other thing, it's really hard to imagine this wouldn't be true. I mean, it's very hard to prove it. We don't know how to prove it. We have a long list of sufficient conditions, but it's really hard to believe that not all regular cardinals up to the cofinality of lambda will show up in the spectrum. And the last conjecture is that for every 2 cardinals, again, this is just by inspection. We look at all the models we can produce, and it's always the case that if theta and chi shows up in the spectrum, then you have a witness, in fact, a close witness to that. So that's all I wanted to say.
Thank you very much, Assaf.